Hi, this is lecture 23B of Differential Equations and Linear Algebra. We've been doing a lot with eigenvalues and eigenvectors recently, mostly with systems of linear differential equations, though I did do one example with a linear difference equation. Lecture 23B, we're doing more examples, 3 new examples of a linear system of difference equations using eigenvalues and eigenvectors again. And just like with the differential equations, we're going to have situations where we have sinks, sources, and saddle points, but now in the discrete case. So, very similar in some ways, but there are some differences, subtle differences in a sense, to pay attention to between the continuous and the discrete cases. Looking at examples here in this lecture. This is going to be a sink for a linear system of difference equations. Here it is. The system of difference equations, not differential equations. xn, the vector xn, whose components are non-boldface xn and yn, is a times xn minus 1, where this right here is the matrix A, and there's xn minus 1. You can multiply this out, and you can also write it like that. A linear system of difference equations. I'm going to use decimal representations for numbers here in this situation, whereas we use non-decimal and fractional representations with the differential equations, because with these examples, we're going to see in most situations where you have examples that are relatively easy to think about and work with, the eigenvalues, when they're real, are positive, but sometimes they're between 0 and 1, and it's going to be easiest to represent those with decimals rather than fractions. We have seen before that one way to write the unique solution of an IVP here, where the initial condition is the vector x sub 0, whose components are x0 and y0, is this way, using a to the nth power. xn, the nth point, the nth iterate, you might say, is the nth power of the matrix A, which I'm also writing here with that nth power, times the initial condition, times x0, and there's a typo I'm noticing right here, right away. This should be 0 is here and here. Okay? That's one way to write the unique solution. But finding a to the n can be difficult. We saw it was relatively easy with diagonal matrices, 2 by 2 diagonal matrices. That actually works for n by n diagonal matrices as well. It gets harder when it's not diagonal. Is there another approach we can use, though, that avoids trying to compute a to the n? Yes, we can use eigenvalues and eigenvectors, just like with the linear systems of differential equations. So let's go ahead and compute the eigenvalues and eigenvectors. In this lecture, 23b, they're all real numbers. In 23a, we were dealing with complex eigenvalues and eigenvectors. We will talk about complex eigenvalues and eigenvectors for these systems as well, the difference equations. So here we have it. Do your standard characteristic polynomial calculation. There's your characteristic polynomial. It's maybe not so clear, but you can factor this as lambda minus 0.8 times lambda minus 0.9. The 2 eigenvalues are indeed between 0 and 1. They're 0.8 and 0.9. Double check this. By the way, I briefly talked about the trace and determinant in the last lecture. That still holds here, this constant term is the determinant of this matrix. Go ahead and calculate the determinant of this matrix. I'm trusting it comes out to 0.72. I did double check these numbers. And the coefficient of lambda in the characteristic equation is negative of the trace of the matrix. Add up the entries on the main diagonal. 0.4 plus 1.3 is 1.7. Put a negative sign in front of it to get negative 1.7 lambda. This is still lambda squared minus the trace times lambda plus the determinant of the matrix. So you again can avoid this kind of stuff like I mentioned in lecture 23a and just jump right to this. Again, it's not so clear that you could factor it this way. If you wanted to, you could use the quadratic formula instead to get these answers. What are the corresponding eigenvectors? Do the same thing here as well as with differential equations. Plug in the lambdas, solve a corresponding homogeneous system. That's always how we calculate eigenvectors. Plug in 0.8. 0.4 minus 0.8 is negative 0.4. 1.3 minus 0.8 is positive 0.5. These are multiples of each other. We get a row of zeros. And if you think of y as a free variable and set it equal to 1, this line means when you add 1.25y to both sides, x would be 1.25 times y, so you get a 1.25 up there, or 5/4. With the eigenvalue 0.9, check the calculations here. you get an eigenvector of 1, 1. Okay? So far, this kind of stuff seems the exact same as what we did with linear systems of differential equations. It's got to change somewhere. Where is it new? Hey, the eigenvectors are linearly independent. We're about to get into the new things here. What have we learned about linearly independent eigenvectors in R2? Two linearly independent eigenvectors in R2. They would form a basis for R2. And I'm talking about regular R2 here. I'm not talking about function spaces. These are constant vectors. I could use them as a basis. And that would mean some things. Everything that we talked about with bases. There's, for example, the unique representation theorem that will allow us to take our arbitrary initial condition vector and write it uniquely as a linear combination of the basis vectors. And maybe that's useful. And it is. It's really useful here. It can also relate it to coordinate vectors and change of coordinate matrices, and we will get there, though not in this lecture. But a unique representation theorem, for any given fixed vector here, think of this as a fixed vector, there exists unique scalars C1 and C2, such that this fixed vector x0 is a linear combination of v1 and v2. If you had particular numbers here, which we will get to, you could solve for C1 and C2. We will do that. But we're thinking about the idea now. In lecture 23a, we talked about why e to the lambda t times v, where lambda was an eigenvalue of a and v was a corresponding eigenvector, solved the differential equation. It was a straight line solution ultimately. That kind of thing doesn't happen here, but something similar does, based on these two things being eigenvectors and 0.8 and 0.9 being eigenvalues. Call them lambda 1 and lambda 2. Think about x1 for the difference equation. That's going to be a times x0. Replace x0 with c1 v1 plus c2 v2. Make that replacement. Then use the linearity of matrix multiplication, which is analogous to linearity of linear transformations, operation preserving. But with matrix multiplication, you really think of it as the distributive property. Distribute the A through and factor out the constants and get this. And then remember, v1 is an eigenvector for A with eigenvalue lambda 1, and v2 is an eigenvector for A with corresponding eigenvalue lambda 2. So I can replace AV1 with lambda 1 times v1 and AV2 with lambda 2 times v2. And once again, I say don't get mixed up. AV1 is a vector. It's a matrix times a vector to give you a vector. Lambda 1 v1 is a vector as well, but it's a scalar times the vector. We're saying these give you the same thing. It's an equality of vectors. Same with AV2 equaling lambda 2 times v2. Iterate. That's what we do with difference equations. x2 would be a squared times x0, or a times x1 if you prefer. Replace x1 with that. Plug that in there for the x1 to get this. Distribute the a through again, factor out the constants again to get this. And then once again, AV1 equals lambda 1 times v1, and AV2 equals lambda 2 times v2. So I get a lambda 1 squared and a lambda 2 squared, and a v1 and a v2 still. Think about that for a minute. You realize x3 is going to be something similar, except the lambda 1 and the lambda 2 will be cubed, etc. In general, the pattern seems to indicate that xn will equal this, where the lambda 1 and lambda 2 are to the nth power, and that is true. So this calculation is analogous to the derivative calculation I did in lecture 23a to verify what I erased there was a solution. When lambda was an eigenvalue and v was a corresponding eigenvector. Same kind of thing here, except it's with difference equations. It's a little simpler. You don't have to think about derivatives, in a sense. So in a sense, that's simpler. And this means, I guess, we didn't have to find a to the n to solve the problem. The eigenvalues and the eigenvectors are good enough for us. Or thought of another way, I suppose we could use this to figure out A, and if we really want to find it. Though we'd have to find C1 and C2 first, and yeah, then it could still be a little tricky. We'd have to set it equal to this and see if that allowed us to solve for A to the nth power. Also note that since lambda 1 and lambda 2 here are less than 1 in absolute value, and in our example, this example there, 0.8 and 0.9, I don't need the absolute value signs there, but I do want to keep them there. Because that being true will imply that this vector approaches the 0 vector as n gets larger and larger, as n goes to infinity. This is a limiting kind of thing I'm thinking about here. A limit. Because when you got two numbers that are between -1 and 1, when you raise them to the nth power, they keep getting closer and closer to 0. Try it. It even works if lambda 1 and lambda 2 are complex numbers and their distance to the origin is less than 1. Maybe you want to try that too. The origin is some sort of sink for this discrete dynamical system. Sink, but wait a minute. With differential equations, we only got sinks when the lambdas were either both negative or had negative real parts, like we talked about in 23a. There's nothing about being negative here for it to be a sink. It's that the absolute value of the numbers has to be less than 1, not negative. That's a subtle difference between the differential equations and the difference equations. Let's go ahead and solve an initial value problem. Let's pick the fixed vector x0 to be -3, 4. My goal is to solve for C1 and C2, set these equal, get a system of linear equations of the unknowns C1 and C2. We can do raw operations and get C1 is -28 and C2 is 32. You can take the time to check these things. I did, for convenience, do a row swap right away without writing it down, because I had 1 right there, so I wanted a 1 in the upper left corner. So I skipped a step in a sense by doing a row swap right away. So plug those in. The unique solution must be this. Plug the numbers in. C1 is -28, C2 is 32, lambda 1 is 0.8, lambda 2 is 0.9. You get this, it simplifies to that. So we're going to graph this. And if we graph it, is it in a phase plane? Yeah, it's not the same kind of phase plane as with differential equations where the solutions are parametric curves. Now the solutions are discrete points. In this picture, that point right there, that's the initial condition, x0. -3, 4 as a point. Of course, it's also got a position vector that I can draw from the origin to that point. x1 is that point right there. For this example, plug in n equals 1. -35 times 0.8 to the first, plus 32 times 0.9 to the first, evidently is a small positive number, first component. And plug in n equals 1 here, -28, 0.8 to the first, plus 32, 0.9 to the first, is evidently a positive number close to 6. Second coordinate at that point. Check it out and try it. And this is going to be x2, x3, etc. These points are moving toward the origin. The origin is an equilibrium point as well. I didn't make a big black dot, but I could have. If the initial condition is 0, 0, you will stay at 0, 0. And if I picked other initial points, like if I picked one down here, I bet we'd get symmetric behavior. It would head in toward the origin. And notice this seems to be parallel to the line of slope 1 to the origin. Is that a coincidence? No, it's not. It's related to the fact that that's parallel to that same line. Like, think about that. You might wonder, well, why not that one? It's related to the sizes of the eigenvalues. Let's do another example. 2 more examples. Here, a source With the differential equations, when I had a sink, I talked about doing a source by negating all the signs of the coefficients of the matrix, the entries of the matrix. Here I'm doing a completely new example. This one here. There's our matrix. I'm going to go quickly through this stuff, and I'm going to show you Mathematica at the end. This will be a shorter lecture than lecture A. Once again, we can write the unique solution that way, and once again, I made a typo that I should fix before I put it online here. These should be zeros. Too much. Copying and pasting is great when you don't make mistakes, but copying and pasting is not so good when you do make mistakes. So I carried my mistakes over, and I'm sure I carried it over into the last example too. There's a characteristic polynomial. You can check the determinant and trace. The trace is 2.4. Determinant is 1.43. Take the time to check that. Again, not so obviously factors this way. Use the quadratic formula to confirm that. That means your two eigenvalues are 1.1 and 1.3, whose absolute values are both bigger than 1. That's why this origin is going to be a source here, because those are both bigger than 1 in absolute value. They're also bigger than 1 overall. But again, dealing with negative eigenvalues in this context does get a little tricky, because with the other example we did similar to that, we get some bouncing back and forth. That's something that doesn't happen with differential equations. When the eigenvalues are negative, or at least one eigenvalue is negative. Corresponding eigenvectors are these. You can take the time to check that. And therefore, your general solution is this. The details are here for you to check, but I'm not going to go through them. 1.1 to the n and 1.3 to the n go to infinity as n goes to infinity. This thing goes off to infinity as n goes to infinity. Should I write the infinity as a vector? The infinity comma infinity vector? Or infinity infinity? Don't worry about it. You can just put an infinity. Goes in the plane, it goes off forever and ever. Away from the origin, arbitrarily, gets arbitrarily far from the origin. That's because of those being bigger than 1, literally bigger than 1, but also bigger than 1 in absolute values, the main thing you want to think about. You can use this to solve initial value problems. I chose a new initial point, negative 0.3, positive 0.4. With the other one, I was negative 3, 4, right? It's going to go away from the origin, so I wanted to pick something close to the origin to start with. You solve the system. You get C1 is 0.6 and C2 is negative 0.2. And here's your unique solution. And if you plot this, the other one kind of almost did a little spiraling at first, though it was not truly spiraling. This one doesn't really do much. x1 is this first, or x0 is that first point there. Negative 0.3, positive 0.4. It does do a little bit of curving at first, but then it looks pretty straight after that point. And indeed, it is parallel, almost, to the line through this vector here. That vector there would point off this direction. Its opposite would point this direction. That line, this would be almost on that line. Not quite, because you're not there at first, but it would be getting closer and closer to that in the big scheme of things, as far as visually at least, how it looks. It's a source. The origin's a source. Do all solutions kind of look like this? Well, they all go away, but they don't necessarily have that particular kind of behavior to them. Do we have saddle points? Yep, here's an example that ends up having a saddle point. Another same mistake from copying and pasting. These should be zeros. Once again, we can avoid doing a to the nth power by using eigenvalues and eigenvectors. The eigenvalues are 0.5 and 2, 1 with an absolute value less than 1, and 1 with an absolute value bigger than 1. That's why this gives us a saddle. Part of the solution goes to 0 as n goes to infinity, and part of it goes to infinity as n goes to infinity. By the way, that source example that I just went over, the points do go back toward the origin as n goes to minus infinity, which you can allow if you want. You can let n be negative. You can have what are called bi-infinite sequences that are solutions. You can allow that if you want. Corresponding eigenvectors are these two, and the general solution is this. This part goes to 0 as n gets bigger. This part does not. In the long term, no matter what C1 and C2 are, at least if C2 is non-zero, this goes to infinity as n goes to infinity, and this part becomes negligible. You head toward points on the line parallel to that vector negative 1, 1, which is this line to the origin with the slope of negative 1. You can think about what's happening based on that formula. But let's solve an initial value problem. I pick this point. This point ends up being close to being on the other line for the other eigenvector. The other line was 1, 1, 4, a line with a slope of 4 through the origin. This is close to being on that. I purposely did that. Solve for C1 and C2. You get 0.98 and negative 0.02. So the unique solution is this. And then you can graph it. Here's the initial point for this one. X0 is right there. 1, 3.9. The line with slope 4 through the origin is just barely above that. This is barely below it. There's x1. Right there. There's x2. Etc. And yeah, this is approaching the line to the origin with the slope of negative 1 as n gets larger and larger. That's the last of the PowerPoint in this quicker lecture. Let's look at Mathematica to end. By the way, real quick, for the lecture 23A where we had complex eigenvalues, Eigensystem will give you the complex eigenvalues and eigenvectors. That's the first system, the spiral sink. Well, that was our main example actually from 23A. Eigenvalues negative 1 plus or minus 2i. For negative 1 plus 2i, the eigenvector was I1. We had that in lecture 23A. But let's now jump back down to the difference equation section. Here's our second example. Here's how it turns out if you use fractions. Remember the eigenvector values were 0.8 and 0.9. Well, there's 0.9, there's 0.8, 9/10 and 4/5. And the eigenvectors are these. One of them was 1, 1. The other one was 1.251, which is 5/4, 1. You can numerically approximate that like this. Percent sign refers to the preceding output. But we also can just plug in decimals to begin with and get the eigenvalues as decimals and the eigenvectors as decimals as well. These, Mathematica does take the time to, when you're using decimals at least, to normalize the vectors to make them unit length. This vector here, negative 0.707, comma negative 0.707, is really an approximation to negative 1 over square root of 2, comma negative 1 over square root of 2. That ends up being a vector of length 1. It's parallel to 1, 1, but in the opposite direction. This vector here, you get if you normalize that vector to have length 1, and then also negated it to get the negative signs. I don't know why it used negative signs instead of positive signs. It used positive signs up there. Doesn't matter, because again, any non-zero multiple of an eigenvector is still an eigenvector. I tried using rsolve value to solve the system. This was for the sink example. It gives you the answer in a pretty weird way. Makes you think, boy, did I do something wrong? Yikes. So what I did instead was I decided to also just define the solution myself based on what I derived in the PowerPoint. And really just see if it's a solution. It doesn't satisfy the initial condition. Is x of 0 negative 3, 4? Yes, it is. By the way, I put the n inside the square brackets. I could have just done it as a subscript if I wanted to. Does it satisfy the difference equation? Is a times x of n minus 1 equal to xn? Doesn't look like it is. These two things look different, but looks can be deceiving. They are actually the same. Because, for example, because it did something funny, instead of an nth power here as an n minus 1 power in all those entries for the 0.8 and the 0.9. But if you do negative 28 times 0.8 to the negative 1, you do get negative 35, like you see here. And if you do 28.8 times 0.9 to the negative 1, you get 32, like you see here. And if you do negative 22.4 from that spot times 0.8 to the negative 1, you do get negative 28. So it is the same as xn. To graph this, because I entered this as a column vector with the palette here, turns out I have to do something a little strange. I have to use something called flatten to see this as a point if I want to plot it with this list plot command. Table considers all the points as n goes to 50 in this case. You can see these points are heading toward the origin here, though relatively slowly, I would say, not as fast as I was expecting initially, which was evident in the plot. This makes the plot through list plot. That was the plot that I showed you in the PowerPoint. And then we can animate it with Manipulate to watch the points head toward the origin as n increases. The origin is a spiral, excuse me, not a spiral. I said spiral because it kind of looks like it's spiraling, but it's not. It's sort of a partial spiral. It's not going around and around the origin. It's heading there as n goes to infinity. In the limit, it heads towards 0, the origin. For the source example, same kind of things can be done. Again, our style value is not so satisfying. Ignore some of this other stuff. I defined xn. Satisfies the initial condition, negative 0.3, comma 0.4. Also can be seen to satisfy the difference equation. This equals this, though you have to do these calculations to double check it. You do see, for example, you get a negative 0.6 here just to match the negative 0.6 here. Again, the reason you have to do that is because Mathematica puts the answer in a strange form with n minus 1 powers instead of n powers. And these points go off to infinity. Here's the plot, and here's the animation. Move slowly at first, then they speed up. Final example is the saddle point, similar kinds of things. Again, the eigensystem, the things in the first list are the eigenvalues, and these are the corresponding eigenvectors. And this vector goes, right here goes with this eigenvalue, and this eigenvector goes with this eigenvalue. Once again, our solve value doesn't work so well, at least as far as giving us a nice looking answer. This initial condition is 1, 3.9. Once again, I can check with these calculations that my xn really does solve the difference equation. A times xn minus 1 here really is the same as xn. Finally, here's the graph as an animation for this one. Points head toward the origin at first, but then the exponential growth takes over. Once they get close to the origin, you get close to that line, and they head along that line as n increases. Yeah, a bit shorter lecture. Thanks for watching.